And we know that this byte is going to be at minus 10 SP because we know that B is located at minus 12 and B2 is just at minus 12 plus 2, which is minus 10. Once we load this byte, then we just go and store it back into whatever space we have decided that T0, or whatever space we've decided that D is going to live at, which in this case is right here. So we load this byte, and then let's look at the store byte instruction. We want to store this value into this byte, so we store the least significant byte into there. Any questions about these two lines of assembly? All right, yeah, in the front. The question is in line 7, where is what stored? Sorry. C. Yeah, the question is, we got told that C was here, but where is C stored? Well, the short answer is that we'll learn about this in our lectures about compilers, but when a compiler or assembler is, or when a compiler is compiling code, it's going to leave itself a symbol table where it can figure out, where it knows the address of every symbol that you find. So the compiler knows where it puts C on the stack. And so the compiler can go and figure out that this value can be computed at compile time. Does that make sense? Yeah. So as an example, we're thinking of the stack pointer as pointing to the top of the space for a stack at this point. So basically, where C is being stored is in these two rows directly on the stack. Does that make sense? Oh, yeah. C is located at minus 52. B is located at minus 12. So the space from minus 52 up to minus 12 is being used to store C, if that makes sense. Sorry, I misheard the question. All right. Oh, question in the front. Yeah, the question is, why is C being stored all the way down at minus 52? And the reason is that C, we're declaring C as 10 ints, right? So how many bytes would 10 integers take up? Yeah. So 10 integers takes up 40 bytes, which means the next 40 rows of this table that are omitted are all for C. Any other questions about this part? All right. If not, then let's go ahead and look at this one. So C4 equals A plus D. So this code is looking kind of similar. So as a reminder, when we have an array, the array's first element is stored at the lowest index, or the lowest memory address, and we go up from there towards larger addresses. And remember that the size of an integer is 16, or the size of an integer is 4. So what we have is 4 bytes for each element of C. And so when we want to do the addressing, we just need to look 4 integers of space past the start of the array, which places us here at negative 36. And so that's how we get this offset of negative 36. And then from there, the only other thing we have to do is load the value of, now that we know the address of what we're going to store, let's load A with this one, load B with this line, and then add them together on line 11, and store our result into the appropriate spot on line 12. Any questions about what we're doing here? The question is, why do we have negative 53? So the answer to why we have a negative 53 is because our pointer, our array, C, is at negative 50. Our pointer C is at negative 52. So D is declared after it. So we're just going to give it the next available space and put it at negative 53 here. Does that make sense? What's LBU? The question is, what is LBU again? Yeah, load byte unsigned. The reason we have this LBU is because remember that the operands kind of determine the type that we're reading something as, right? Or yeah. So most importantly, D is an unsigned integer, which means that we need to use LBU to load it, otherwise we'll get the wrong result. Right. So any questions about what's happened here before looking at our next part? Oh yeah, in the front. Hmm? Yeah, SP here is equivalent to the X2 register. Yeah, so basically what SP means is stack pointer. So it points us to the stack in some manner. In this case, what we're going to think about it, or how we're going to think about it for this example is that, do you remember in Justin's lecture when we had the stack frames all at the top of the stack? We're just going to imagine that we have one of those and we're using the space in that. Yeah, it points into memory. Right. So, any further questions? Oh, in the front. Yeah, the question is, what happens if we do regular load byte instead of load byte unsigned on line 10? Well, when we do a regular load byte, what happens is we're going to read this as a signed value. So this 0x72 is either going to get read as a positive, or it could be read as a negative value in some cases. So this will affect us if this byte happens to start with an 8 or higher, because in that case, what will happen is we will sign extend it and cause a negative number. So instead of computing A plus D, we would end up computing a completely wrong, if that makes sense. All right. So if there are any further questions, please put them on Ed. I'll be looking at Ed periodically up here. So if there are any questions, I can go ahead and. All right. I do see some questions on Ed that are pretty good. So I guess the first question here is that on this slide, where is negative 53 SP coming from? And the answer to where negative 53 SP is coming from is just that it is the next available byte underneath the start of this array, C. So we place C from negative 52 up until negative 13, which means that the next available space is negative 53. Right. And then here is our, oops. And then this is just a final visualization of what's happening. When we compute, we load this blue area into this register marked in blue. We load this pink byte into this register marked in pink. We add them together, and then we get this value, 0x77, which we store at our offset computed earlier. So now, let's go ahead and look at our variable array indexing. So on the next line, we're doing C bracket A equals 20, which means that we're going to be doing something a little more complicated. So the first thing to look at this line is that we have an immediate. So we're just going to go ahead and put the immediate here for future use. And remember that 20 in decimal is 0x14 in hex. So now we have our value that we want to store into memory located at this register T0. So the next thing we need to do is we need the value of A, right? So to load the value of A, the first thing we do is we figure out where A is. Well, remember that we put A at -4 SP. So that's the offset that we're going to use here. So now we have -4 SP. And let's just load it into whatever register we have available. So T1. So we'll load A into register T1. And remember that and once we have that, now we have our index, or A is the number 5. But 5 is not exactly what we want, right? So when we have an index of 5, what does C do for us when we have 5 in an array, right? Notice what C has done has nicely given us the offset from pointer arithmetic. But in RISC-V, we don't have such luxuries. Notice how a difference of 5 items turned into a difference of 20 bytes. And the reason for this is because each int is 4. So what we do now is we can multiply our offset by 4. So if we multiply the number 5 by 4, now we get the amount of bytes that we need to jump. So we can do this with the SLLI instruction. Remember that shifting is sort of equivalent to multiplying by 2. And then we have our new computed value. And lastly, and now the next thing we do is we need to figure out what the offset of C is. So because C is at -52 SP, we want an offset 14 away from -52 SP. We're going to have to add both 52 and SP onto T1. And then we will compute our desired offset. Finally, once we have this desired offset, we can store word directly into this row. And we'll overwrite that row with our desired data. All right, any questions about this one? All right, if there are no, oh, in the front. Mhm. Yeah, so the question is about this syntax here on line 15. And yeah, that's exactly what it means. It means T1 we take the value in T1, shift it by 2, or multiply by 4, and then we store it back into T1. So that's how we get the. If you wanted to shift to the right, then what you would use is the other instruction. So the shift right arithmetic or shift right logical. So. All right. All right. If not, then at this point, we've hit our midpoint of the lecture. And let's take a 2 or 3 minute break and come back for control. All right. Welcome back after our break to the second half of this lecture. So let's go ahead and talk about control in RISC-V. So, all right. All right. Up to this point so far, we've gotten quite a nice set of features. We know how to do math. We know how to work with memory. But one thing we don't know is how to actually do like structuring our program, right? Because all we've learned is that the lines execute one after another. We go from one line to the next line to the next line. And so what this means is that what we have is the ability to do this. But control flow means being able to change the next line our program runs, right? For example, an if statement means that if we satisfy this condition, we go inside the if statement. And if we don't satisfy the condition, we run the line after the if statement. Likewise, when we call a function, we always go to the first line of the function instead of going to the next line. And when we return, we come back. So these places where we run code, where we run a line of code other than immediately the next line, are what we call jumps. Jumps can either be unconditional, where we just go ahead and always jump no matter what, or jumps can be conditional, where only sometimes we make this jump, and otherwise we would have just taken the next line directly. So in C, we've all seen these as, say, if else, if else, for loops, while loops, and function calls, etc. So we want to replicate these in RISC-V now. So let's think about what instructions we can use. And oops. All right. Sorry about that. I messed up the animation. But we get two different kinds of syntax here. So we have we have the unconditional jump, which is just jump to a label. And we'll get to what a label is in a little bit, but basically they're just a little thing that you can put in front of a line of code to give that line of code a name. Meanwhile, what we have for a branch instruction is we can have BEQ, RS1, RS2 label. So sometimes if we want to do comparisons, we might need arguments. So we have two register arguments here for comparisons. So with this syntax introduced, let's go ahead and just look at, say, an example of something. So looking at the branch if equal instruction, BEQ stands for branch if equal. And what it does is if the value stored in RS1 equals the value stored in RS2, then what we'll do is we will jump to the label. So we'll learn more about the program counter in lectures starting in the future. But basically, all you have to think about what PC means for now is it tells us what line of code we're going to run. So we change what line of code that we're going to run if these are equal. Otherwise, we just go to the next line. And similarly, we have branch not equal, where if these registers are not equal, then we go to the line specified by label. Otherwise, we go to the next line. So it's a little hard to understand what these things do without seeing examples of code. So here's an example. Assume we have this snippet of C code, and these registers have these variables inside of them. And this is the label syntax we were talking about earlier. So for a label, we literally just put a name and a colon in front of a line of code to mark it with that label. I've gone ahead and done some nice indenting on the code to make it look nice, but do note this is literally just like 7 spaces here in front of the J. It's not like outside of the code. All right. So if we assume this mapping, let's take a moment and look at our two things. And let's think about if either of them work for our code. So I'll give everyone just a minute or so, or like a few seconds to look at this and kind of make an opinion on which one or both or neither that you think is correct. All right, so let's do the same hum thing we had in the previous lecture. So as a reminder, hum proportionally loudly to which one you think is correct. So hum if you think that the code in A is correct. Hum if you think the code in B is correct. Hum if you think that both of them are correct. And hum if you think neither of them are correct. Okay, I think, at least according to how loud the hum sounded on here, I think we got the correct thing. Both of them are valid, but we have different trade-offs in each case. For our solution in A, we get that our branch condition looks exactly like what we wrote in C code. We are directly comparing if I and J are equal by comparing the registers x13 and x14. However, because we're doing jumps, we ended up in a situation where the result of our code, what code actually gets run, ended up in a different order. In part B, we write the if statement in a way by negating it, but now we have the add line coming before the subtraction line. So in either case, it depends on what you think is more readable. This is mostly a stylistic choice on if you would rather negate the branch and have one case before the other, as you would in C code, or if you would rather keep the condition the same, but flip the order of the two arms. All right. Any questions about this example? Yeah, in the front. The question is, where's the label stored? And what the label does is once the assembler reads it, the label just tells the assembler, hey, make a note, keep track that this is here. And then once we get into converting this into ones and zeros, you'll see that the labels basically just get converted into numbers. So the label will basically get converted into a line number of the code. So your computer will remember that like, oh, the else label showed up on like line 5. So everywhere else appears, I can replace it with line 5, basically, if that makes sense. I think in Monday's lecture, it'll be made more clear where labels are actually stored. Any other questions looking at this example? All right. If not, then let's look at another example here. And this example is kind of just showing us that we have different options in writing code. So it's basically exactly the same as earlier. We just removed the else arm. And now, if we apply the same two strategies, either keeping the condition the same or keeping the order of the arms the same, we notice something. Even though we've written two still valid programs, one of them uses one less instruction. And also, in my opinion, it's kind of easier to read what happens here. Kind of do this line only if the things are not equal. It might be you might have a different opinion, and that's fine. But just one note is that negations might end up giving us code that is easier to read. Right. Any questions about this second example? All right. If not, then here's a table with all of the rest of the branch instructions. So we have BEQ and BNE, which stand for branch if equal and branch if not equal. Then we have BLT, BGE, branch if less than, branch if greater than. Then we have branch BLTU and BGEU, branch if less than unsigned, and branch if greater than or equal unsigned. And lastly, we have this J, which is just unconditional jumping. So, does anybody, oh, question in the front? Yes, the question is, for BLT, are we comparing if RS1 is less than RS2 or if RS2 is less than RS1? And the answer is that RS1 will always be on the left-hand side of the comparison and RS2 will always be on the right. So all of these are like RS1, if RS2 is less than RS2, go to label for all of these. Does that make sense? Another question in the front. Yeah, that's a great question. This is actually exactly what we're about to talk about next. There is no branch strictly greater than or branch less than or equal to. That's kind of weird, right? Why don't we have this? Well, remember that in risk 5, the R stands for reduced. So they do exist as pseudo instructions, but this also means that we can convert it into an actual instruction. So your request for branch strictly greater than or branch less than or equal to, well, I think we have BLE at home. Does anybody want to give a thought on what BLE at home might be? Yeah, in the front. Yeah, we can do a negation by swapping two arguments here, and then we can use a different branch instruction. So notice that RS1 is less than or equal to RS2 is exactly the same as RS2 is strictly greater than RS1. Does anyone have any questions about this? Or does anybody want to think about this for a little bit to convince themselves that this is true? Wait. Did I write the wrong thing? Did I make a typo? What happened? Oh, that should be a B. Yeah, wait, that's a BGE. I just made a typo on the slide. Yeah. So we can get our instructions just by flipping the order of arguments to our other instructions. And so what we have is we don't need them. Right. So before moving on to loops, does anyone have any questions about branches or jumps? In the back. Yeah. The question is, do you have to do something different for the equals case? And the answer to that is that the equals case is covered, right? So what we have is, let's just take some numbers, for example, and think about the behavior we would want. So if we have rs1 equal to 1, rs2 equal to 2, then 1 is less than or equal to 2, so we want to jump. And flipping it, 2 is greater than or equal to 1, so we want to jump. If they were equal, 1 and 1, well, BLE would branch if they were equal, so we jump. And likewise, 1 equals 1, so we also jump. So basically what we have is, if you plug in some numbers and compare, you'll see that the cases in which this jumps and the cases in which this jumps are exactly the same. Does that make sense? Any other questions before looking at loops? In the front? Yeah, so the question is, why do we have branch less than and branch greater than or equal to as our actual instructions, and the other ones as our not equal instructions? And honestly, I have no idea. There might be some piece of history that I don't know. Why we have BLT and BGE instead of BGT and BGE. Okay. Okay, Justin. Thank you for your joke. All right. I mean, this is like a reasonable explanation. It's as reasonable as I could come up with. Yeah, but this is just decided by the people who designed the spec. Any other questions before I quickly look at that stuff? All right. If there are no further questions, then let's go ahead and look at loops. So loops are slightly more complicated, right? In C, we have a few different kinds of loops. We have while loops, we have for loops, we have do while loops. From 61A, we've learned that each loop can be rewritten as one of the other two. So one key point that we're going to learn about here is, let's go ahead and try to just write one type of loop with branches. So in this case, we're going to write the for loop with branches. And then with that, you should be able to convert every single loop into a different kind of loop and then write it out. And then another note is, we'll be looking at goto. C actually does have something similar to what loops or what jumps in RISC-V look like. But the warning is, don't actually use goto in real life. It's really bad practice. But yeah, so we're going to go ahead and start converting C to assembly here. So we have this C code on the left. And the first thing that we're going to want to do is turn our loop into a while loop. So notice here that with the for loop, it's exactly the same as we take this statement, put it out front, I equals 0, I equals 0. And then we just say, while I is less than 20, this condition in the middle. And then we put this I++ as the last line of the while loop. Does everyone agree that this is what the while loop version of this for loop is? All right. After writing it as a while loop, what we're going to do is we're going to turn it into an infinite loop, because infinite loops are easier to implement because you kind of just you unconditionally jump from here up to here. So it simplifies our logic a little bit. So what we have is while true, if I is greater than or equal to 20, we exit the loop, right? This while loop stays in the loop while I is less than 20, which means the moment I becomes greater than or equal to 20, we're going to want to jump out of the loop. Otherwise, we keep the exact same loop body and move it over here. So does anybody have any questions about the C conversion that we've done before we go ahead and look at the RISC-V version? Yeah, in the front. Mm-hmm. Yeah, the question is, we have this conditional jump still inside, and basically the benefit of this is mostly that it's easier to conceptualize on a first learning about loop spaces, but you are right that you can use conditional jumps, and we'll see one example if we have time at the end of lecture. Any other questions? All right. If not, then let's move this code over to the side and try to make something similar in assembly. So out of convenience, we're going to be using these registers to denote these C variables. T0 will be in, or R will be in T0, sum will be in T1, and I will be in T2. Right. So the first thing that we're going to want to do is just set up this infinite loop. So to set up an infinite loop, what we need is a pointer to, or a label for the start of the loop, and a label for the end of the loop. Once we have that, what we can do is we can just put this J loop at the bottom, and now we've got our infinite loop structure. Does that make sense? Where we have this J loop always goes back up to this loop, so we are in our infinite loop. Then what we do is we look at this fi is greater than or equal to 20 statement. And to set this up, how could we do this? Well, remember that BGE takes in 2 registers as arguments. And we don't really have an immediate version of BGE. So what do we have to do when we don't have the ability to take an immediate? Well, what we do is we just take the number 20, this immediate that we want, we put it into some register, some T3, and then we just compare the 2 registers here. All right, and with that, that is basically the entirety of the loop. Does anyone have any questions about setting up the loop? Right. If not, then then we have this line finished and this line finished. And now we have just filling in the rest of the loop. This lecture ended a little earlier than I expected, with 15 minutes left in content. So there is some extra optional content at the end of lecture I can unhide if anyone would like to see. Or if anybody has any questions up to this point, or would like to see the solution to this, feel free to ask. But I guess the first thing, does anybody have any questions about setting up a loop in C with this format? All right. If not, then the next thing that, if not, then the next thing is, let's go ahead and look at the solution to this, or with the rest of the code. Or right. Oops, I did forget about one last section in my PowerPoint. Sorry about that. And yeah, so congratulations on getting through the introduction to RISC-V. Here's a summary of everything we've seen so far. We have register-to-register arithmetic instructions. We have register immediate instructions. the memory instructions, and the control instructions. As a note, these are just a subset of the instructions that are fully on the C reference card or the RISC-V reference card on our website. We've talked about, one moment. We've talked about all the features that we're going to see, but there are a few other things that will be interesting to see, and those are on the reference card. Question in the front. Yes. The question was, what is the difference between add and add I again? And the difference was that add adds two registers together. Meanwhile, add I adds a register and an immediate together. An immediate is like a constant. Yeah. Yep. All right. Any other questions about RISC-V? All right. Oh, in the front again. Yeah, the question is, what format is an immediate in? Is it in binary? Is it in hex, etc.? And the answer is that you can write the immediate in any format you want. So you can write like 0b whatever, or 0x whatever, or just the number in decimal. Any other questions? The question is, what is the size of a label? And that is more complicated to answer. The reasoning is that it depends on really how much code you have written, how big a label is. And what happens is that when we end up doing translations from labels into binary, on Monday, you'll get to see what labels actually resolve to. But for now, you can think of them as kind of magical names for lines of code. Yeah, over there. For back here. It depends on the implementation of your compiler and assembler where it's stored at. But this would be stored on the stack and offset and take up 80 bytes on the stack. It could be SP-84 is one possibility. There are other possibilities of how to manage a stack that we'll see in tomorrow's lecture. Oh, over here. Yeah, the question is, this loop colon and this end colon, are they part of the code, or are they like outside? The answer is they are just code. I like put a bunch of spaces at the front of the other lines to make it line up nicely. This is one stylistic choice that you can make. One other common way of writing this is, let me get my mouse over here. One other common way that some people choose to write this is to put a loop here and then indent it like that. This is another valid way of writing the code. In either way, the label attaches to the next instruction that comes after it. Another question up front. Sorry, there's a little background noise. Can you say it one more time? Yeah. Okay, good question. Yeah, good question. So the question is, in this label loop, the question is, in this label loop, is everything attached to this label, or is it just the instruction? And the answer is that all right. And the answer is that what happens is this label is attached only to this instruction, but what happens is execution continues here, right? So once you actually end up here, you run the next instruction in sequence anyways. And so that's why it's just this instruction and not everything under it. And the other question that came with that was, what if you would like to end the code, or what if you would like to end the function without writing an explicit end label? And you don't have to write this end label. This end label here is only here so that we have somewhere to break to. Oh, yes, in the front. Hmm? Ah. Yeah. The question is, will we need to have this li20 in the loop every time? And in this example, we do have it in the loop every time because we don't have some tools that we're learning about in tomorrow's lecture. In tomorrow's lecture, we're going to see that you could, for example, as long as you know that you're not going to change T3 from this line to this line, right? You could move this line outside of the loop and save yourself a bunch of work. But there are certain rules we need to follow with what registers are allowed to change at what time, which we'll learn about tomorrow. Yep, exactly. Yeah. Yeah, the question is, are you not allowed to just do the control comparison with an immediate directly? And the answer is that no, you're not really allowed to do this comparison directly. The only branch instructions that exist in our base set of RISC-V take in 2 registers. So you have to load it into a register. All right. Any other questions? All right.
It's like before.
Okay.
This one really confused me. Like the part where you're on like the SL the left shift by 2.
Shift to the left.
I didn't understand that. Yeah. Do you understand it?
Well, you have to put.
So for here, like when we are storing the string, how do we know how many bytes